Hello, and welcome to Space for Sleep. On the evening of April 13th, 2029, a point of light will appear among the stars above parts of Europe, Africa, and Western Asia. At first, it may not look extraordinary. It will not blaze like a meteor. It will not grow a tail like a comet. It will not fill the sky, and no surface detail will be visible to the unaided eye. It will resemble a moderately bright star that has somehow forgotten to remain still. Watch it for a little while, and the difference will become unmistakable. The point will move. It will glide across the star field quickly enough for a patient observer to notice its progress in real time. Over minutes, its position will change. Over hours, it will cross a broad arc of sky and fade as it continues away. That moving point will be an asteroid called Apophis. Its average width is about 340 meters, roughly the height of the Eiffel Tower. Radar observations suggest that its longest dimension may extend to at least 450 meters. It may be elongated or composed of two joined lobes, more like a rough stone peanut than a sphere. On that April night, it will pass only about 32,000 kilometers above Earth's surface. The Moon is roughly 12 times farther away. Many satellites in geosynchronous orbits circle at an altitude of about 36,000 kilometers. Apophis will come closer to the surface than that familiar ring of communications and weather spacecraft. The phrase "closer than many satellites" is therefore true, but it needs care. Apophis will not pass below every satellite. Thousands of spacecraft orbit much closer to Earth, only a few hundred or a few thousand kilometers above us. Other satellites travel far beyond the geosynchronous region, and Apophis will not sweep through the crowded equatorial band like a stone through a necklace. Its path is inclined, carefully calculated, and safely separated from the most densely occupied satellite region. It will not strike Earth. It will not strike the satellites. It will not end civilization. The certainty of those statements is part of what makes the night remarkable. Human beings will be able to look upward at a large asteroid passing unusually close and know, not through hope or superstition, but through decades of measurement and mathematics, that it will miss. The encounter will be safe. It will also be violent in a quieter sense. Earth's gravity will seize the asteroid's trajectory and bend it. The side of Apophis nearest our planet will be pulled slightly more strongly than the far side. The uneven pull may stretch the asteroid, alter its tumbling rotation, shift loose stones, trigger landslides, and produce small internal tremors. For a few hours, Earth will turn a near-Earth asteroid into a natural laboratory. Spacecraft will watch. Radar beams will cross the distance. Telescopes around the world will record the changing light. And perhaps a small instrument resting directly on the asteroid will feel the ground move as the planet passes beneath it. This will be one of the rare occasions when a large asteroid comes to us, allowing an experiment that would normally require years of travel into deep space. Yet the calm scientific event of 2029 began with a very different emotion. It began with uncertainty. And for several days in December 2004, uncertainty placed Earth directly inside the path of Apophis. The asteroid was discovered on June 19, 2004, by Roy Tucker, David Thalin, and Fabrizio Bernardi at Kitt Peak National Observatory in Arizona. At first, it carried the temporary designation 2004MN4. It was a faint moving speck. Discovering an asteroid does not immediately reveal its future. A telescope records a position against the background stars. Later observations record another position, and then another. From that short arc of motion, astronomers estimate an orbit. With only a few measurements, many possible orbits may fit. Imagine seeing a car through 3 narrow gaps in a wall. From the first glimpse, the car is near one streetlight. From the second, it has shifted. From the third, it has moved again. You can estimate its direction, but you may not know its exact speed, its distance, or whether the road curves beyond the wall. An asteroid discovered far away presents a similar problem. Though the geometry is three-dimensional and the motion is shaped by the gravity of the Sun, planets, and Moon, the first observations of Apophis covered only 2 nights. Weather and technical difficulties interrupted the work. For months, the asteroid was effectively lost in the crowded sky. Then it was recovered in December by observers in Australia. The new measurements allowed orbit computers to project the object forward toward April 13, 2029. The date itself sounded theatrical. Friday the 13th. The result was worse. Some of the possible orbits passed close to Earth. A smaller subset passed through Earth. As more observations arrived, the estimated region of uncertainty narrowed. Normally, that is reassuring. But an odd thing can happen during the early tracking of a potentially dangerous asteroid. The impact probability can rise even while knowledge improves. At first, the possible future positions may fill an enormous region of space, and Earth occupies only a tiny fraction of it. The calculated chance of impact is small. As new data shrink the uncertainty, the predicted positions may become concentrated around Earth. The region becomes smaller, yet Earth fills more of it. The probability rises. This does not mean the asteroid has changed course. It means the fog around the course is clearing in an uncomfortable direction. By December 27, 2004, the calculated probability that Apophis would strike Earth in 2029 had reached about 2.7%, roughly 1 chance in 37. For an everyday risk, 2.7% may sound small. For a 340-meter asteroid, it was enormous. Most newly discovered near-Earth objects briefly appear on automated risk tables at probabilities so tiny that they are difficult to communicate meaningfully. Their uncertain paths may touch Earth many decades in the future, but later observations almost always move the projected orbit away. Apophis was different. It became the first object to reach level 4 on the Torino scale, a public communication system ranging from 0 to 10. Level 0 means no meaningful danger. Level 1 usually means a routine discovery that deserves tracking but no public concern. Level 4 describes a close encounter meriting attention because the current data indicate at least a 1% chance of collision capable of regional devastation. No asteroid had received such a rating before. Behind this simple number was a network of observatories, orbit specialists, automated systems, and researchers working through holidays while much of the world was focused on other news. The Indian Ocean tsunami occurred on December 26th, caused by an earthquake rather than an asteroid. Human attention was already fixed on catastrophe. Now another possible disaster had appeared in orbital calculations. The early media language grew rapidly. Apophis had not yet received its mythological name, but the idea of a doomsday asteroid was irresistible. Some reports treated probability as prediction. Others treated uncertainty as official confusion. The science was less dramatic and more disciplined. No one knew that Apophis would hit. Astronomers knew that the available measurements had not yet ruled it out. Those statements are not the same. The job was to find more data. Astronomers searched older photographs of the sky, looking for images taken before the official discovery. If Apophis had happened to cross a telescope's field of view, its faint trace could extend the observational arc backward and sharply improve the orbit. This practice is called precovery. An asteroid can exist unnoticed inside an image for years. The photons arrived, the detector recorded them, and only later does anyone know where to look. Precovery observations were found. Together with new measurements, they moved the predicted 2029 path away from Earth. The impact possibility disappeared. Apophis would come extraordinarily close, but it would miss. The first danger was over before most people had learned enough orbital mechanics to understand why it had seemed real. Yet the story did not end. A close pass can change an asteroid's future. Earth's gravity would bend the orbit so strongly that tiny differences in the 2029 trajectory could determine where Apophis returned years later. The problem moved from one date to a sequence of dates: 2036, the 2050s, 2068, and between Apophis and those possible futures lay narrow regions of space with an ominous name: gravitational keyholes. A keyhole is not a physical doorway floating beside Earth. It is a small region in the plane of a close encounter. If an asteroid passes through that region at the right position and time, Earth's gravity changes its orbit into a resonant path that can lead to a future collision. The asteroid misses during the first encounter. The flyby acts like a precise gravitational turn. After a certain number of orbits around the Sun, asteroid and Earth return to the same place at the same time. An impact occurs later because of where the asteroid passed earlier. For Apophis, one widely discussed possibility involved April 13, 2036, exactly 7 years after the 2029 encounter. To hit Earth in 2036, Apophis would first have needed to pass through a very small keyhole during the earlier flyby. The 2029 miss was safe, but its exact geometry still mattered. This transformed the asteroid into a lesson about scale. Apophis itself is hundreds of meters wide. The region of possible positions before a close encounter can stretch across thousands of kilometers. A dangerous keyhole may be only kilometers or less across, depending on the return scenario. The difference between harmless passage and future impact can be smaller than a city inside the vast geometry of interplanetary space. This is why orbit determination is not finished when a telescope learns where an asteroid is today. Scientists must understand how uncertainty grows, how planetary gravity amplifies it, and how subtle forces shift the object over years. The Sun's gravity dominates Apophis, but not every relevant effect is purely gravitational. Sunlight can slowly move an asteroid. When sunlight warms the surface, the asteroid later radiates that energy as infrared heat. The outgoing photons carry momentum. Because the surface heats and cools unevenly as the asteroid rotates, the recoil does not cancel perfectly. This tiny push is called the Yarkovsky effect. At any instant, it is extraordinarily weak. Over years and decades, it can shift an asteroid's position enough to matter when the object approaches a narrow keyhole. To predict the effect, scientists need information about spin direction, rotation, shape, thermal inertia, surface roughness, and composition. A dark, slowly cooling surface responds differently from bright dust. A tumbling asteroid radiates heat differently from a simple spinning sphere. Apophis does not rotate neatly like Earth. It turns in a complex non-principal axis state. One component of its motion takes a little more than 30 hours, while a slower rocking motion unfolds across many days. Its changing orientation complicates the thermal force. This was one reason the possible 2068 impact remained under discussion longer than the earlier dates. Better optical measurements, radar ranging, and physical models gradually constrained the Yarkovsky drift. In March 2021, Apophis passed Earth at a much greater distance than it will in 2029. The encounter was not visually spectacular, but it offered an essential observing opportunity. NASA's 70-meter Goldstone antenna transmitted radar toward the asteroid. The Green Bank telescope received the echoes in a bistatic arrangement. Radar does something optical images cannot do as directly. A telescope measures the object's direction on the sky. Radar measures distance and motion along the line of sight with extraordinary precision by timing the returning signal and measuring its frequency shift. The 2021 campaign determined Apophis's distance to within roughly a few hundred meters, even though the asteroid was about 17 million kilometers away. When all available observations were combined, The future uncertainty collapsed. The 2068 impact was ruled out. So were all other impacts for at least the next century. Apophis was removed from NASA's Century Risk Table and from the European Risk List. The asteroid had traveled from faint discovery to record hazard rating to planetary defense icon to scientifically valuable non-threat. Nothing about the physical asteroid had become safer during those years. Only our knowledge had changed. This is one of the central truths of planetary defense. A probability is not a property painted on an asteroid. It is a description of what we know about the possible relationship between its orbit and Earth. New evidence can raise it. New evidence can lower it. The goal is not to produce comforting numbers. The goal is to produce accurate ones early enough to act. Apophis demonstrated that process in public. The first estimates were alarming because the data allowed an impact. The later estimates became reassuring because the data excluded it. There was no cover-up, reversal, or failed prediction. There was a narrowing path through uncertainty. By 2021, the path no longer touched Earth for 100 years or more. The approaching night of 2029 could now be planned as a scientific event. And planning mattered, because an object of this size comes this close only on timescales measured in thousands of years. Humanity happened to discover Apophis early enough to prepare. We know the date. We know the approximate path. We know the asteroid will be visible without a telescope across a vast region of the Eastern Hemisphere. We are building spacecraft to meet it. The same asteroid that once represented an uncertain threat has become a scheduled experiment. The transformation is almost too neat. But the experiment begins with a more basic question. What exactly is coming toward us? Apophis is classified as a stony, or S-type, asteroid. Spectral measurements indicate silicate minerals and a mixture of rocky material with nickel and iron. Its spectral properties are broadly consistent with ordinary chondrite meteorites, the common stones that fall to Earth after surviving atmospheric entry. This does not mean Apophis is simply one enormous meteorite waiting in space. Its structure may be very different from a solid laboratory specimen. Many small asteroids are rubble piles, collections of boulders, gravel, dust, and fractured material held together mainly by their own weak gravity, contact forces, and perhaps small amounts of cohesion between grains. The phrase rubble pile sounds unstable, as though the asteroid should fall apart. In space, weak gravity can be enough. There is no ocean pulling pieces downward with terrestrial weight. A rock that would weigh a ton on Earth exerts only a tiny force on the surface of a small asteroid. Fragments can rest against one another in shapes that would collapse under stronger gravity. The asteroid may contain large voids. Its interior may be layered by size. Fine material can migrate into cavities. Boulders can touch at a few load-bearing points. Some regions may be compacted while others remain loose. Radar suggests that Apophis is elongated and perhaps bilobed. It may consist of two major masses joined together, the result of earlier collisions or slow reassembly after disruption. Its average diameter is about 340 meters, but that number hides the irregular geometry. A long axis of at least 450 meters would make one direction substantially larger than another. Its density is not known precisely. Its internal strength is not known. Its porosity is not known. These properties matter for planetary defense. A solid monolith responds to an impact differently from a loose aggregate. A kinetic impactor can transfer momentum directly, but ejected material can add a recoil that strengthens the deflection. The amount depends on surface and interior properties. A gravity tractor, a spacecraft hovering nearby and tugging gently over years, depends on mass. A nuclear device used only in an extreme scenario would interact differently with porous rock than with coherent metal. Before attempting to move an asteroid, one wants to understand what kind of object it is. Apophis will allow scientists to study those properties while Earth itself applies a force. The planet will not merely deflect the orbit. It may expose the asteroid's hidden mechanical nature. If the body is loose, tidal stresses may rearrange surface material. If some regions are more cohesive, they may remain unchanged. If the spin state shifts, slopes across the surface will change, and grains that were stable may begin to slide. A fresh patch may appear where old space-weathered material moves aside. Boulders may roll. Fine dust may lift briefly in the asteroid's weak gravity. Small particles may escape entirely, or very little may happen at the surface, revealing greater strength than some models predict. All of these outcomes are valuable. The Earth encounter becomes a stress test. The asteroid is the specimen. The planet supplies the force. And unlike a laboratory sample, Apophis has been evolving for more than 4.5 billion years. It formed from material left over after the planets began to assemble. Its earliest history probably began in the main asteroid belt between Mars and Jupiter. There, countless fragments collided. Some broke apart, some reaccumulated. The gravitational influence of Jupiter slowly moved certain objects into orbital resonances that changed their paths. Collisions could also alter speed enough to feed fragments toward planet-crossing space. Over millions of years, Apophis entered the inner solar system. Before 2029, it belongs to the Aten class of near-Earth asteroids, objects whose orbital periods are shorter than 1 year and whose paths cross Earth's orbit. It completes a circuit around the Sun in a little less than an Earth year. After the flyby, Earth's gravity will enlarge the asteroid's solar orbit. Its period will become a little longer than a year, and its classification will change from Aten to Apollo. This reclassification sounds bureaucratic, but it describes a real transformation. The same object will approach Earth on one kind of solar orbit and leave on another. A close planetary encounter is a gravity assist, whether or not a spacecraft planner arranged it. As Apophis falls into Earth's gravitational field, it accelerates relative to our planet. As it climbs away, it slows relative to Earth. In a simple Earth-centered picture, the speed before and after is nearly the same, but the direction changes. In the Sun-centered picture, Earth is moving around the Sun while the encounter occurs. The asteroid exchanges a tiny amount of orbital energy and angular momentum with the planet. Earth's own motion changes by an immeasurably small amount. Apophis's orbit changes dramatically. The imbalance reflects mass. Earth is enormously more massive than the asteroid. The exchange is mutual, but almost all visible consequence belongs to Apophis. Its path bends. Its year lengthens. Its rotation may change. Its surface may rearrange. The world that leaves will not be quite the world that arrived. This gives the encounter a natural before and after structure. To understand the transformation, scientists must observe Apophis before closest approach, throughout the strongest tidal forcing, and afterward. One spacecraft arriving only after the event can map the result, but must rely on older observations for the initial state. One arriving before can watch the change directly. By 2026, 2 major missions occupy complementary roles. The European Space Agency's Rapid Apophis mission for space safety, known as Ramses, is being built to rendezvous with the asteroid before the close approach. NASA's OSIRIS-APEX is already in flight and will meet Apophis after the Earth encounter. Together with observatories across the planet, they may create the most complete record ever made of a small body undergoing a close planetary flyby. Ramses carries urgency in its name. The asteroid will not wait for a delayed launch. To reach Apophis before April 2029, the mission must leave Earth in spring 2028 and rendezvous around February 2029. This is an unusually unforgiving schedule for interplanetary engineering. Most science missions can tolerate a delay of months or years, though the cost may be severe. Ramses must arrive before nature performs the experiment. Missing the launch window would mean missing the event that justifies the mission. The commitment to the mission was made at the European Ministerial Meeting in November 2025. By the summer of 2026, construction of the spacecraft structure had begun. The central tube, a carbon fiber backbone around which the spacecraft is assembled, stood in a cleanroom in Bremen. Japan joined the project. JAXA is providing contributions including lightweight solar arrays, an infrared instrument, and launch on an H-3 rocket. This partnership gives Ramses a path to Apophis and brings experience from asteroid missions such as Hayabusa and Hayabusa 2. Ramses is designed not simply to photograph a passing rock. It will measure shape, surface, orbit, rotation, mass, density, porosity, and internal clues before and after Earth's gravity acts. It will release small companion spacecraft. One of them, called Don Quixote, is intended to reach the surface before the close pass. A shoebox-sized instrument on Apophis would experience something no spacecraft has experienced before, an asteroid's ground responding to a close encounter with Earth. It could measure motion directly. It could feel vibrations from shifting blocks or internal adjustment. It could observe whether loose material moves as gravity gradients and rotation change. The name Don Quixote carries a quiet joke. An earlier European planetary defense concept used the same literary theme for a proposed asteroid deflection demonstration. Now a small spacecraft bearing the name may ride an asteroid safely past Earth, listening for quakes. Another companion can observe from a separate position, providing stereo views and independent measurements. The main Ramses spacecraft will watch the asteroid grow larger as Earth approaches in the background. From Apophis, Earth will not appear as a small blue point. It will expand into an enormous world. At closest approach, the planet will span a large part of the sky. Clouds, oceans, and continents may be visible to cameras. The asteroid will pass through regions where Earth's gravity changes rapidly across its own body. For an observer fixed to the surface, the experience would be strange. There is no atmosphere to carry sound. There is almost no gravity. The sun still shines. Earth rises or sweeps across the sky depending on the observer's location and the asteroid's tumbling orientation. The planet's pull changes the direction considered downhill. Stones resting for ages may find themselves on new slopes. If seismic vibrations occur, they travel through contacts between boulders and grains. The waves may be complex, scattering through voids and irregular structure. A surface instrument could reveal whether Apophis behaves like a coherent body, a loose aggregate, or something between. Ramses may arrive before humans on Earth can see the asteroid without optical aid. It will establish the initial state. It will map boulders and craters. It will measure spin and wobble. Then, as April 13th approaches, every later image can be compared with that baseline. A changed boulder position becomes evidence. A fresh bright patch becomes evidence. A shifted rotation period becomes evidence. A different tumbling motion becomes evidence. Nature will not repeat the test. The measurements must be ready the first time. Osiris Apex approaches from another direction in this story. The spacecraft was once Osiris Rex, built to visit the carbon-rich asteroid Bennu, map it, collect a sample, and return that sample to Earth. It completed the central mission successfully in September 2023, releasing a capsule containing material from Bennu into the Utah desert. The spacecraft itself remained healthy and retained fuel. Rather than end the mission, NASA redirected it toward Apophis. The renamed Osiris Apex must survive repeated passages closer to the Sun than its original design expected. Engineers adjusted the spacecraft's orientation to protect sensitive components, using its solar arrays and structure as a shield. It passed those early tests. The mission remains active. OSIRIS-APEX will begin imaging Apophis before the close encounter from a distance, but it will not be beside the asteroid during the most intense part of the flyby in the same way Ramses is planned to be. It will rendezvous after the event, around June 2029 according to current planning. This makes it the specialist in consequences. It carries cameras, spectrometers, and a laser altimeter proven at Bennu. It can map the post-encounter surface in detail and compare it with radar, telescope, and Ramses measurements from before and during the flyby. It will remain with Apophis for many months. Near the end of its work, the spacecraft is expected to descend to only a few meters above the surface and fire its thrusters downward. At Bennu, a similar maneuver was associated with sample collection. At Apophis, no sample will be returned, but the gas jets can disturb dust and expose less weathered material below. Cameras and spectrometers can then examine what the disturbance reveals. This introduces a second controlled experiment after Earth's natural one. First, the planet applies tidal stress across the entire asteroid. Then a spacecraft applies a local blast to the surface. The comparison may reveal how deeply the Earth encounter disturbed the regolith and whether fresh material differs from the old exterior. OSIRIS-APEX also brings a remarkable continuity. A machine launched in 2016 to study Bennu will still be working at another asteroid 13 years later. Its instruments will compare a carbon-rich rubble pile with a stony one. Its team will carry lessons about unexpected boulders, weak surfaces, particle ejection, and small body navigation from one target to another. Bennu surprised scientists repeatedly. Its surface was rougher than expected. It ejected particles naturally. It responded to contact in ways that showed extremely weak surface material. Apophis may surprise us differently. A mission designed around one asteroid cannot assume the next behaves the same. That is the reason direct observation matters. Planetary defense cannot rely on one generic asteroid. Each body has a history. Each has structure. Each rotates. Each carries its own arrangement of rock, metal, dust, voids, and fractures. A deflection method must push the real object, not an ideal sphere in an equation. Apophis will become one of the best characterized potentially hazardous asteroids, even though it poses no known threat for at least a century. That knowledge will apply to other objects that may not offer such a generous warning. The encounter is therefore about more than one famous name. It is rehearsal. It is calibration. It is an opportunity to learn how the solar system's leftover building blocks behave when brought close to a planet. And it will occur in full view of Earth. The visible passage will begin before closest approach, as the asteroid brightens while moving into a favorable geometry. Observers in much of Europe, Africa, and parts of Asia will have the best chance, weather and local light pollution permitting. It will not appear equally bright everywhere, and it will not remain visible for the same duration from every location. The exact path among the constellations depends on the observer's position because the asteroid will be so close that parallax becomes enormous. Parallax is the apparent shift of a nearby object against a distant background when viewed from different places. Hold a finger in front of your face and alternate between your left and right eye. The finger appears to jump against the room. Apophis will be the finger. Earth itself will be the separation between observers. Someone in Spain and someone in South Africa will not see the asteroid against exactly the same stars at the same time. Their lines of sight will differ by degrees. This is unusual in popular sky events. A distant planet appears in nearly the same constellation for everyone. The moon shifts slightly with location. Apophis will be close enough for geography to reshape the route visibly. Local predictions will therefore matter. A generic map of the sky will not be enough. Astronomical organizations will publish tracks tailored to cities and regions. Mobile applications and planetarium software will update as the orbit becomes even more precise. The asteroid is expected to brighten to roughly the visibility of a modest naked-eye star under good conditions. It will not resemble the Moon. It will not cast a shadow. It will not show a disk. The drama lies in motion and knowledge. A point of light will move because a 4.5 billion-year-old body is passing between Earth and the region occupied by geosynchronous spacecraft. At closest approach, its apparent motion may be quick enough to notice over seconds or minutes, depending on location and viewing geometry. Binoculars will make it easier to follow in light-polluted areas. A small telescope can show a sharper point, but high magnification can make tracking harder because the asteroid crosses the narrow field rapidly. The best experience may be simple: a dark place, a clear horizon, a correct chart, several minutes of patient watching. The asteroid will not arrive from nowhere. Telescopes will have followed it for years, then days, then hours. Yet naked-eye visibility changes the psychological scale. An orbital solution is abstract. A moving light is immediate. People who have never used a telescope may watch the same object that once carried a 1 in 37 impact probability. They will know it is safe. They will also know that a slightly different path would have created a different history. This combination, proximity without danger, makes the event rare. A threatening asteroid should not be approached as entertainment. A distant, harmless asteroid is difficult to feel. Apophis occupies the narrow space between them. It will pass close enough to reveal the architecture of planetary defense while remaining far enough away to let us observe calmly. The date adds cultural tension. Friday the 13th has accumulated centuries of superstition in parts of the world. The number itself has no effect on orbital mechanics. Earth and Apophis do not know the calendar, yet the coincidence helped fix the event in public memory. The name deepened the symbolism. Apophis is the Greek form of Apep, a serpent associated in ancient Egyptian mythology with chaos and the nightly struggle against the sun's order. The discoverers chose the name after the asteroid's orbit had become notable. They were also familiar with a fictional character called Apophis, but the official meaning reaches back to mythology. A dark serpent approaching Earth on Friday the 13th sounds written for a disaster film. Reality is more interesting. The object named for chaos became a demonstration of order. Its motion follows gravity. Its uncertainty follows statistics. Its risk changed as measurements improved. Its safe passage can be predicted years in advance. The mythological creature tried to devour the sun each night. The asteroid will simply borrow a little energy from Earth's motion and continue around the sun on a changed orbit. The name may draw attention, but the science removes fear. That does not mean the hypothetical impact would have been harmless. An asteroid hundreds of meters across could cause regional catastrophe if it struck Earth. It would not be a planet killer. It would not reproduce the extinction event associated with the asteroid that ended the age of non-avian dinosaurs. That impactor was roughly 10 kilometers across, tens of times larger in diameter and vastly greater in mass. Apophis belongs to a different scale. Its consequences would depend on speed, angle, density, structure, and location. A stony asteroid entering the atmosphere at many kilometers per second experiences enormous pressure and heating. It may fragment, but an object this large can deliver a large fraction of its energy to the surface or lower atmosphere. The released energy would likely be measured in hundreds or perhaps more than 1,000 megatons of TNT equivalent, depending on assumptions. That is enough to destroy a large region. An impact near a city would be catastrophic. An ocean impact could generate dangerous waves near some coastlines, though the popular image of one global wall of water crossing every ocean is too simple. Tsunami effects depend strongly on water depth, impact angle, distance, and coastal geometry. A land impact would excavate a crater and generate blast, heat, ejecta, and seismic effects. Dust could enter the atmosphere, but an asteroid of this size is not expected to produce the global darkness associated with a 10-kilometer impactor. Regional devastation is already severe enough. There is no need to exaggerate it into extinction. The distinction matters because planetary defense decisions depend on scale. A 20-meter object may explode in the atmosphere and shatter windows. A 50-meter object can devastate a city or broad rural region. A few hundred-meter object can threaten a nation-sized area depending on circumstances. A kilometer-scale asteroid raises global concerns. A 10-kilometer object belongs to mass extinction history. Different sizes require different survey priorities, warning times, and response methods. Apophis sits in a range that is dangerous enough to demand prevention and common enough that the population is not fully cataloged. Many kilometer-scale near-Earth asteroids are known. The smaller population is harder to complete because faint objects can remain invisible until geometry brings them closer. A 300-meter asteroid reflects little sunlight at planetary distances. If it approaches from the direction of the sun, ground-based optical surveys may not see it until late. Some spend most of their time far from Earth and appear faint. Others cross crowded star fields. Weather, moon brightness, and telescope coverage create gaps. The Veris C. Rubin Observatory, which began its main survey in 2026, will repeatedly image much of the southern sky and discover large numbers of moving objects. Infrared space telescopes can find dark asteroids by detecting heat rather than relying only on reflected light. Radar then refines nearby objects when geometry permits. No single instrument completes planetary defense. The system is layered. Wide surveys discover. Follow-up telescopes prevent newly found objects from becoming lost. The Minor Planet Center gathers measurements. Orbit computers assess future encounters. Radar sharpens distance and velocity. Infrared data estimates size. Spectroscopy suggests composition. Light curves reveal rotation. Spacecraft test structure and deflection. International organizations coordinate warnings and observations. Apophis touched nearly every part of this system. It was discovered optically. It was recovered after a gap. Recovery images changed the orbit. Radar removed future risk. A global exercise later used Apophis as a stand-in for a newly discovered hazard, deliberately hiding its known identity from parts of the response network to test whether the system could rediscover and assess it. The exercise succeeded. The asteroid was found, tracked, characterized, and ruled harmless again. In that sense, Apophis has already served planetary defense twice. First as a real, uncertain object, then as a controlled rehearsal. In 2029, it will serve a third time as a physical experiment. This progression also shows why the sentence, "the system worked," must be used carefully. The system worked for an object found 25 years before close approach. It worked because telescopes were available and the asteroid became observable repeatedly. It worked because the predicted impact disappeared. A future object may be discovered with less warning. It may approach from a difficult direction. It may remain uncertain because radar geometry is poor. It may not resolve safely. Planetary defense is not finished because Apophis misses. Apophis shows what success looks like when discovery comes early. The longer the warning, the gentler the required deflection. This principle is more important than raw spacecraft power. To prevent an impact, an asteroid does not need to be pushed far away from the solar system. Its arrival time needs to change enough that Earth is elsewhere when it crosses our orbit. Earth moves roughly 30 kilometers along its orbit every second. A tiny change in asteroid speed applied years in advance can accumulate into thousands of kilometers of separation. Push early, and the required change can be almost imperceptible. Wait until the final days, and no practical spacecraft can move a large asteroid far enough. Planetary defense is therefore an exercise in timing. Detection is part of deflection. Orbit precision is part of deflection. International decision-making is part of deflection. A rocket on the launch pad is only the visible end of a long chain. The DART mission demonstrated one link. In September 2022, NASA deliberately struck the small asteroid Moon Dimorphos with a spacecraft. Dimorphos posed no danger to Earth. It orbited a larger asteroid called Didymos, creating a convenient test system. The impact shortened Dimorphos's orbital period around Didymos by more than half an hour. Ejected material enhanced the momentum transfer beyond the direct push of the spacecraft. Later analyses refined the enhancement and showed that the response depended on how much debris escaped and how the body deformed. The lesson was not that one identical spacecraft can move every dangerous asteroid. The lesson was that kinetic impact is a real, measurable technique. A future threat like Apophis in size would require a mission designed around its mass, composition, warning time, and desired displacement. Several impactors might be used. A reconnaissance mission might arrive first. If warning were long enough, a gravity tractor could hover near the asteroid and use mutual gravity to pull it gradually. Ion beam concepts could direct exhaust toward the surface without contact. In some scenarios, concentrated sunlight or surface alteration could change the Yarkovsky force over years. Nuclear devices remain a possible last resort tool for large objects or short warning, preferably used to impart momentum rather than fragment an asteroid unpredictably. No method is universally best. The correct response depends on the problem, and the first question is always the same. What is the orbit? Apophis taught that a small orbital uncertainty can dominate every other discussion. There is no reason to design a deflection while the possible paths still spread across millions of kilometers unless the schedule demands early preparation. There is also danger in waiting for impossible certainty. Decision makers must act under probability. A mission can take years to approve, build, launch, and arrive. If the impact probability is significant and the warning time is shrinking, preparation may begin before final confirmation. Apophis briefly forced experts to think through that uncomfortable territory. A 1 in 37 chance is not a certain impact. It is far too large to ignore. What would governments have done if the probability had remained at that level? Who would lead? Who would pay? Would a deflection attempt risk moving the projected impact point across national borders before eliminating it? How would information be communicated without panic or false reassurance? What if one country disagreed with the orbital analysis? What if a mission failed? These questions are not solved by physics alone. Planetary defense is planetary in the political sense as well as the astronomical one. An asteroid does not recognize borders. An impact corridor can cross oceans and continents as uncertainty changes. A deflection benefits Earth as a whole. The decisions may still be made by particular agencies and governments with different interests. Apophis gave the world time to build coordination structures before a real confirmed threat appears. The International Asteroid Warning Network links observers and analysts. The Space Mission Planning Advisory Group brings space agencies together to consider response. National planetary defense offices connect science with emergency planning. Exercises simulate discovery, impact probability growth, possible evacuation, and mission options. These efforts are quieter than rocket launches. They may prove equally important. A perfectly designed impactor launched too late is useless. A correct orbit hidden inside poor communication can still produce disaster. A false alarm handled badly can weaken trust before the next discovery. Apophis is a case study in how uncertainty should be explained. The impact probability rose because observations narrowed the orbit around Earth. Then it fell because older and newer data moved the orbit away. A rising probability did not mean the asteroid was steering toward us. A falling probability did not mean officials had changed the answer to calm the public. Both changes followed evidence. The honest language is simple. This is what the current data allow. This is what they exclude. This is how much uncertainty remains. This is when new observations may reduce it. A risk table is not prophecy. It is a living calculation. Apophis now has one of the best-known near-term close-approach trajectories of any asteroid. The 2021 radar data reduced the predicted 2029 position uncertainty to only a few kilometers. Additional measurements before the encounter will refine it further. Yet predicting the post-flyby rotation and surface response remains much harder than predicting the center of mass path. Orbital mechanics can be precise while asteroid geology remains uncertain. We know where the body will go. We do not know exactly what the body will become. That difference between trajectory and transformation is one reason the 2029 event cannot be replaced by simulation alone. Computers can model a rubble pile as thousands or millions of particles. Each particle feels gravity, contact forces, friction, and perhaps cohesion. Researchers can rotate the model, apply Earth's tidal field, and predict where movement might begin. But the answer depends on assumptions. How angular are the blocks? How much fine dust fills the gaps? What is the friction angle? Do tiny electrostatic or van der Waals forces help grains cling together? Is the interior homogeneous? Does a denser lobe pull differently from a porous one? Where is the center of mass relative to the shape? What orientation will the asteroid present during closest approach? Apophis's complex tumble makes that final question especially important. If the long axis points toward Earth, the tidal stress differs from the case in which it lies sideways. A boulder on one slope may become unstable while an identical boulder elsewhere remains fixed. The encounter may alter the tumble in a way that changes the orientation during later hours, creating feedback between spin and stress. Models predict possibilities rather than one guaranteed spectacle. The phrase asteroid quake can also mislead if it conjures an Earth-like earthquake. Earthquakes occur when stress releases along faults in a planet with strong gravity and a coherent crust. Apophis may transmit vibrations through a loose assembly of blocks. A small rearrangement can send pulses across contacts. A boulder landing after a brief hop can shake neighboring material. Tidal deformation can change internal pressure between grains. The resulting seismic environment may resemble a granular body settling rather than a continent breaking. A surface seismometer could distinguish those possibilities. If vibrations travel efficiently, the interior may be more connected or compact. If they damp rapidly, the body may be loose and highly porous. Resonant frequencies can reveal overall structure much as a tap on an object reveals whether it is solid or hollow. There is no need for the asteroid to split apart for the experiment to succeed. In fact, complete disruption is not expected. Earth's closest pull is strong enough to modify Apophis, but far below the extreme encounter required to tear a body of this size into a stream under most plausible structures. The Roche limit is often mentioned in discussions of tidal breakup, but it is not one simple boundary for irregular rubble piles on fast flybys. The outcome depends on density, strength, spin, trajectory, and how long the force acts. Apophis passes quickly. The strongest tides last for a limited interval. A few landslides, a changed spin, or measurable internal strain would be scientifically rich. Even a null result matters. If detailed before and after maps show no movement, then cohesion or internal arrangement prevented the predicted changes. That would constrain models used for other asteroids. Science does not require the dramatic result. It requires a discriminating measurement. The same principle applies to the asteroid's surface color. Space weathering gradually changes exposed rock. Solar wind ions, micrometeoroid impacts, and radiation alter grains over time. Freshly exposed material may differ in brightness or spectrum from the mature surface. A landslide can reveal a less weathered patch. Ramses can record the initial appearance. Osiris-Apex can map the aftermath. If color changes align with predicted unstable slopes, the connection becomes strong. If freshly exposed regions appear without obvious movement, another process may be involved. The asteroid's thermal behavior may change too. A surface covered in fine dust stores and releases heat differently from exposed rock. Infrared measurements before and after can detect altered thermal inertia. This matters for the Yarkovsky effect, because thermal emission slowly modifies the future orbit. The close approach therefore links short-term tides with long-term trajectory. Earth changes the spin and surface. The new spin and surface change how sunlight pushes the asteroid afterward. A complete post-encounter orbit model must account for both. This is a beautiful example of scales joining together. A landslide lasting seconds changes thermal properties. Thermal properties alter photon recoil across years. Photon recoil shifts position across kilometers. A kilometer can determine whether a future keyhole is crossed. For Apophis, current calculations show no impact for at least a century. But understanding these connections improves predictions for every other asteroid. The close approach also changes how easy Apophis is to observe. Near closest passage, it becomes bright and fast. Soon after, from Earth's perspective, it moves into a region of sky close to the Sun, making optical observation difficult. This creates a brief gap at exactly the time scientists want to know what changed. Ramses, traveling with the asteroid, is designed to avoid that limitation. Osiris-Apex can continue approaching from space. Ground radar can observe during selected windows depending on geometry, scheduling, and transmitter capability. Radar images do not resemble ordinary photographs. They are built from delay and Doppler information. One dimension can represent distance from the radar. The other represents velocity created by rotation. A lobe moving slightly toward Earth shifts frequency one way, while the opposite side shifts another. From repeated views, scientists reconstruct shape and spin. At the extreme closeness of 2029, radar echoes will be powerful compared with previous campaigns. Goldstone planning is already underway. The return signal can reveal features much smaller than the overall asteroid. Repeated radar images can show rotation changing across the encounter. Ranging can refine the trajectory to extraordinary accuracy. Ground-based optical telescopes contribute different information. Brightness variations create a light curve. As an irregular asteroid rotates, its projected area and surface markings change. The pattern reveals rotation periods and shape constraints. Spectroscopy splits reflected sunlight into wavelengths, identifying broad mineral features. Polarimetry measures how the surface alters the orientation of light, offering clues about texture and grain size. Thermal infrared observations reveal temperature and thermal inertia. Stellar occultations provide another powerful method. If Apophis passes in front of a distant star, the star briefly disappears. Observers spread across a region record the exact time of disappearance and reappearance. Each station measures one chord across the asteroid's silhouette. Many chords combine into a detailed outline. Because Apophis moves rapidly and its apparent path shifts strongly with location, occultation campaigns require precise coordination. A small error in prediction can place observers outside the shadow. During the close approach, the geometry may allow unusually detailed shape measurements. Amateur astronomers can contribute. Modern cameras, accurate clocks, and shared networks make small telescopes useful for timing, astrometry, and light curves. The event may become the largest coordinated public observing campaign for a near-Earth asteroid. Yet the naked eye view will remain the emotional center. To understand what a person will see, it helps to compare Apophis with familiar moving lights. An aircraft crosses the sky quickly, but it flashes, changes brightness, and often makes sound. A satellite moves steadily and silently, usually taking minutes to cross from horizon to horizon. It can brighten or fade as it enters Earth's shadow. The International Space Station can be extremely bright and obvious. Apophis may resemble a fainter satellite at first glance. The difference is distance and nature. A satellite is a machine a few meters or tens of meters across in Earth orbit. Apophis is a natural body hundreds of meters wide following a solar orbit, only temporarily passing through near-Earth space. A meteor moves much faster, appearing and vanishing in seconds. Apophis will remain visible long enough to track. A planet moves too slowly for its motion among stars to be noticed during one evening without careful measurement. Apophis occupies the middle, fast enough to move before your eyes, slow enough to watch. For many observers, finding it may be harder than seeing it. A magnitude near 3 is visible from dark locations, but can be washed out by city lights, haze, moon glow, or low altitude. Binoculars will help. Public observatories may organize events. News broadcasts may display live tracks. Websites will show the asteroid's predicted path, but local observers should use updated regional guidance because parallax shifts it strongly. In Madrid, the route will differ from that in Cairo. In London, local twilight and weather may matter. In Cape Town, the viewing geometry will be different again. Some locations will see the asteroid rise, brighten, and accelerate. Others will catch only part of the passage. Clouds will hide it from many people, as clouds hide every astronomical event regardless of rarity. For those who miss it, spacecraft and telescopes will provide images. But no recording can reproduce the awareness of standing beneath the trajectory. 32,000 kilometers sounds vast on human scales. A commercial aircraft flies around 10 kilometers high. The International Space Station orbits around 400 kilometers. Navigation satellites occupy altitudes of tens of thousands of kilometers. The Moon is about 384,000 kilometers away on average. Apophis will pass at about 1/12th lunar distance from the surface and only several Earth radii above us. If Earth were reduced to the size of a basketball, Apophis would pass only about the length of a room away, depending on the scale chosen, while the Moon would be much farther. The asteroid itself would be microscopic in that model. This combination explains why it can come so close without appearing large. Angular size depends on physical size divided by distance. A 340-meter object at 32,000 kilometers subtends only a tiny fraction of a degree, far below naked eye resolution. Its visibility comes from reflected sunlight, not apparent width. Even large telescopes will usually record a point unless adaptive optics, radar, or spacecraft provide closer detail. The popular phrase, "the size of the Eiffel Tower," helps imagine consequences but can create the false expectation of a tower-shaped object looming overhead. There will be no visible rock face, no shadow crossing continents, no roar. The asteroid passes in vacuum. Sound cannot travel from it to Earth. Its gravity has no noticeable effect on people, oceans, or the planet. Earth dominates the encounter. Apophis does not pull tides in our seas. We pull tides in Apophis. The mass ratio is so extreme that the asteroid is physically transformed while Earth continues almost unchanged. This reverses the disaster narrative. In impact stories, the asteroid changes Earth. In 2029, Earth changes the asteroid. The encounter is therefore best understood not as a near miss in the final seconds. It is a close encounter already solved. The excitement lies in knowledge and transformation. The phrase close call remains meaningful historically because the early probability was real within the data. But by the night of passage, there is no unresolved chance hanging over observers. The path is known. The geometry is safe. The asteroid does not suddenly veer because someone looks away. Gravity is predictable. Small body orbits are chaotic over very long times after planetary encounters, but 2029 lies close enough and is measured well enough for certainty. What does it mean to say no impact for at least 100 years? It does not mean the asteroid becomes dangerous immediately after the century ends. Orbit predictions are reported over a defined interval. Beyond that, accumulated uncertainty and future encounters may limit statements. Continued observations extend knowledge. After 2029, the changed orbit will be measured directly, making later predictions far more precise. Ramses and Osiris Apex will help determine the new spin and thermal properties needed for Yarkovsky modeling. The asteroid may remain harmless far beyond the published horizon. Scientists avoid claiming eternity because orbital systems evolve. The responsible statement is bounded. No known impact risk for at least a century. This is stronger than saying probably safe in 2029. It is an exclusion based on detailed tracking. The chance of a random, unobserved object striking Earth in that period is a separate issue. Apophis's safety does not protect Earth from other asteroids. Planetary defense must survey the entire population. This distinction is often lost when a famous object leaves the risk list. People may ask why scientists continue spending money if the dangerous asteroid has been ruled out. The answer is that Apophis was one member of a large population. Near-Earth objects are continually discovered. Most are small. Some pass close. A few enter risk tables temporarily. The goal is to find the next Apophis earlier and characterize it faster. There is also a population of long-period comets whose warning times can be shorter, though large comet impacts are much less frequent. An asteroid survey is not a one-time census. Orbits evolve. Telescopes improve. Faint objects become visible under new geometry. The sky must be watched continuously. Discovery rates can create the appearance that danger is increasing. In reality, finding more objects usually reduces risk because unknown hazards become known trajectories. A newly listed asteroid may frighten the public, but an undiscovered asteroid is not safer. Knowledge turns surprise into planning. Apophis is the clearest example. Before June 2004, the asteroid existed on the same general path without a name. No one worried because no one knew. After discovery, concern rose. After measurement, concern disappeared. The physical universe did not become more or less dangerous during those stages. Human awareness changed. This is why a night watching Apophis can feel philosophical. We will see an object that was once mathematically capable of impact within our uncertainty and is now mathematically excluded from impact within our knowledge. The point of light represents both ignorance and precision. It will also represent patience. The final safety determination required 17 years after discovery, not because astronomers did nothing in between, but because the best measurements were available when the asteroid returned to observable positions. Near-Earth objects can spend years near the sun in our sky, or far away and faint. Radar works only when they come close enough. Orbit improvement is paced by celestial geometry. Science sometimes waits for nature to provide the next baseline. Apophis returned in 2021. Radar collapsed the uncertainty. The waiting ended. The same rhythm continues toward 2029. Missions must launch at precise times. Earth rotates into the viewing geometry. The asteroid arrives once. Afterward, no human alive is likely to witness another known asteroid of comparable size, making such a close naked-eye passage. Events of this class occur perhaps once every several thousand years on average. The exact estimate depends on the population model and the chosen size and distance thresholds. The meaningful conclusion is simple. It is rare on the scale of recorded history. Ancient people may have lived through similar passages without recognizing them. A dark asteroid might have crossed the sky unnoticed, especially if weather, daylight, or viewing geometry were unfavorable. No telescope tracked it. No orbit was calculated. No spacecraft waited nearby. 2029 is unprecedented not necessarily because nature has never done this during human existence, but because humans know in advance and possess tools to study it. Prediction changes an event. A total solar eclipse observed without warning is a terrifying disappearance of the sun. The same eclipse predicted to the second becomes a gathering for science and wonder. Apophis follows that pattern. A close asteroid discovered only during passage would produce alarm. A close asteroid predicted and cleared of impact risk becomes a shared astronomical night. The comparison with eclipses is useful in another way. An eclipse follows an extremely precise path across Earth, and observers travel to the narrow zone of totality. Apophis will have a visibility geometry rather than one narrow shadow, and people across a vast region can see it. Its path among stars will differ with location. Communities may gather in dark parks. Schools may hold evening observations. Planetariums may explain why the asteroid is safe. The event can become the public face of planetary defense. This creates an opportunity and a risk. The opportunity is education. People can learn that asteroids are not supernatural omens, that probabilities evolve with data, and that deflection is physically possible with sufficient warning. The risk is sensationalism. A headline saying, "Asteroid closer than satellites," can imply collision with spacecraft. A graphic can draw the asteroid enormously out of scale. An animation can make a safe miss look like a last-second dodge. The date and name make fear easy to sell. Clear communication must preserve wonder without inventing danger. The accurate facts are already dramatic. A stony body the height of the Eiffel Tower, 32,000 kilometers above the surface, visible to naked eyes. Earth gravity changing its orbit and perhaps its geology. 2 spacecraft missions studying the encounter. A former record impact probability now reduced to 0 for at least a century. No embellishment is needed. The satellite comparison deserves particular care because it is the source of the title. Geostationary orbit is a special circular orbit above Earth's equator. A satellite there takes 1 sidereal day to circle the planet, matching Earth's rotation and appearing fixed above 1 longitude. Weather and communications satellites use this region. Their altitude is close to 35,800 kilometers. Apophis's closest altitude is lower, but it does not travel along the geostationary ring. Its encounter plane is inclined relative to the equator. When it crosses the equatorial plane, it is not occupying the densely populated geostationary belt. Satellite operators know the trajectory and can assess conjunctions precisely. NASA states that the flyby poses no danger to satellites or astronauts. This does not mean the asteroid will thread randomly between unsuspecting spacecraft. Space is large. Even crowded orbital regions contain enormous separations. The asteroid's path is known years ahead. The title communicates altitude, not collision risk. Some navigation satellites orbit lower than the geostationary belt, around 20,000 kilometers. Apophis remains above them at closest altitude, though 3-dimensional geometry again matters. Low Earth satellites are much closer to the planet. High elliptical spacecraft can travel both below and above the asteroid's distance. There is no single altitude called our satellites. The most accurate phrase is that Apophis will pass closer to Earth than many geosynchronous satellites. Precision does not weaken the image. It makes it trustworthy. At closest approach, radio signals between Earth and the asteroid would take only a fraction of a second one way. Spacecraft commands usually travel across minutes or hours in deep space missions. Near Earth, Ramses and its companions will communicate with much shorter light time, though operations must still be planned carefully because the geometry changes rapidly. The asteroid's apparent position will race across the sky from ground antennas. Tracking systems must move. Doppler shifts change quickly. The line of sight may pass between stations. Networks across continents can hand over communication and observation. The encounter is a navigation challenge as well as a science event. Ramses must remain near Apophis while Earth's gravity bends both trajectories. A spacecraft accompanying a small asteroid is not orbiting it in the familiar way a satellite orbits Earth. Apophis's gravity is extremely weak, and stable close motion is strongly perturbed by the Sun and Earth. Mission designers use carefully chosen relative trajectories, hovering arcs, fly-arounds, and station keeping. During closest approach, Earth becomes the dominant local gravitational actor. The spacecraft and asteroid follow similar but not identical paths. Small differences can grow. Navigation must preserve safe observation distances without using thruster exhaust that contaminates the surface or disturbs measurements unintentionally. Companion CubeSats add complexity. They must be deployed at the right time, establish communication, and survive an environment no mission has sampled directly. A surface CubeSat cannot rely on strong gravity to hold it down. Touchdown must avoid bouncing back into space. Anchoring, gentle contact, or carefully controlled descent may be required. Once on the surface, the changing effective gravity during the Earth encounter could lighten, shift, or reorient the instrument. What counts as up and down on Apophis is a combination of the asteroid's weak gravity, rotation, shape, and Earth's tidal field. A seismometer must remain coupled to the ground. A camera needs a useful view. Antennas must communicate despite tumbling orientation. Power must last. The mission schedule is compressed. This is planetary defense engineering under a fixed celestial deadline. If Ramses succeeds, its data will complement Osiris Apex in a way rarely available. Ramses sees before and during. Osiris Apex sees after in prolonged detail. Ground observatories connect all phases. One mission can verify another. If a surface change appears in post-flyby maps, Ramses may show when it occurred. If a vibration is recorded, optical data may reveal a landslide at the same time. If the spin changes, radar and spacecraft navigation can measure it independently. This network reduces ambiguity. The natural experiment becomes reproducible through multiple instruments, even though the event itself occurs once. It also prepares missions for an actual hazardous object. A reconnaissance spacecraft sent toward a threat may need to determine mass and structure rapidly. Ramses tests fast development. Small companions test distributed measurements. Osiris Apex tests repurposing an existing spacecraft for planetary defense science. Ground campaigns test international coordination. The lessons extend from hardware to organization. One day, a discovered asteroid may not be safe. Its probability may remain high. A spacecraft may need to launch before every uncertainty is resolved. The Apophis program builds experience without the pressure of an impending impact. This is the best time to practice. Emergency procedures are safest when rehearsed before an emergency. The asteroid itself provides a target representative of many potentially hazardous objects. Its stony composition is common. Its size is regionally dangerous. Its irregular shape and tumble are realistic complications. Its close approach amplifies the signals scientists need. The encounter is a full-scale drill conducted by gravity, and Earth has been preparing for it since 2004. Preparation for asteroid hazards did not begin with Apophis. For most of history, the idea that stones could fall from the sky was itself disputed. Meteorites were often treated as folklore or misunderstood atmospheric phenomena until carefully witnessed falls and chemical analysis established their extraterrestrial origin. The craters on Earth were also misread. Wind, volcanoes, and erosion can create circular structures. The planet continually recycles its surface through water, ice, vegetation, and plate tectonics. Ancient impact scars become buried or distorted. The Moon preserved a clearer record. Its craters showed that collisions shaped planetary surfaces. Still, the idea that impacts could influence biological history became widely accepted only after evidence connected a global layer rich in iridium with the extinction at the end of the Cretaceous period. A buried crater at Chicxulub completed the picture. The solar system was no longer a clockwork museum in which major collisions belonged only to formation. Impacts had happened during the Age of Life. They could happen again. Comet Shoemaker-Levy 9 made the possibility visible in 1994. Jupiter's gravity had torn the comet into fragments. One after another, the pieces struck the giant planet, producing dark scars larger than Earth. For the first time, humanity watched a predicted collision between solar system bodies. The target was Jupiter, not Earth. The lesson was still immediate. Objects can be discovered before impact. Their motion can be calculated. The impact can be observed. A natural event once associated with myth became a scheduled scientific campaign. The same year saw growing support for systematic searches for near-Earth objects. Survey programs expanded. Digital detectors replaced slower photographic methods. Automated software compared images and identified moving points. The number of known near-Earth asteroids rose rapidly. This did not reveal a newly dangerous solar system. It revealed the population that had always existed. Then came smaller reminders. In 1908, an atmospheric explosion above the Tunguska region of Siberia flattened forest across more than 2,000 square kilometers. No crater was required. The incoming body, probably tens of meters across, broke apart and released energy in the air. The remote location limited human casualties. In February 2013, an object roughly 20 meters wide entered above Chelyabinsk in Russia. It arrived from a direction near the sun and had not been detected in advance. The brilliant fireball was recorded by countless cameras. The shock wave shattered windows across a wide area and injured more than 1,000 people, mainly through flying glass. The asteroid was far smaller than Apophis. Its effects came from an airburst high above the surface. Chelyabinsk demonstrated the lower end of consequential impact hazards and the difficulty of finding small sunward objects. On the same day, by coincidence, a different asteroid passed close to Earth as predicted. The public saw one event that had been forecast and another that had not. Planetary defense must handle both. Large objects are easier to detect because they are brighter, but rarer. Small objects are more numerous, faint, and often discovered late. Apophis sits between, large enough to cause regional devastation, small enough to have remained unknown until 2004, bright enough during favorable approaches for detailed tracking, complex enough to test modern methods. The asteroid's discovery also arrived during an era when public access to risk tables was growing. Anyone with an internet connection could watch impact probabilities change. This transparency is valuable, but raw numbers without context can become a source of fear. A newly discovered object may show dozens of possible future impact dates at minuscule probabilities. The list can look like a schedule. In reality, it is a set of mathematical solutions not yet excluded. Most disappear after follow-up. Apophis taught observers how probability corridors evolve. Suppose a telescope measures an asteroid's position with tiny errors. Each angular coordinate has uncertainty. Distance may be poorly known. Velocity is inferred from change. Orbit fitting software creates a cloud of possible states consistent with the data. These are sometimes represented by virtual asteroids, each following a slightly different path. The cloud stretches over time. Planetary encounters distort it. If part of the cloud intersects Earth, a probability appears. Additional observations reshape the cloud. An impact solution can vanish without any force acting on the asteroid. The mathematics also explains why one should not simply average all possible paths and declare the center safe. A narrow tail of the distribution can still cross Earth. Orbit analysts propagate the full uncertainty and account for nonlinear effects. Close encounters make the problem especially nonlinear. A small difference before Earth can become a large difference afterward because gravity bends neighboring paths by different amounts. Keyholes are the most vivid consequence. The 2029 encounter acts as a magnifying lens for orbital uncertainty. This is why a few meters or kilometers in the flyby plane once mattered to dates decades later. The word keyhole suggests exactness, but the size and location depend on models. Solar radiation pressure, thermal forces, planetary ephemerides, and asteroid mass all enter. The Earth is not a point mass. Its equatorial bulge and uneven gravity can matter in extremely close calculations. The Moon also pulls. Other planets shape the path over longer time. Relativity provides tiny corrections. Large asteroids contribute minute gravitational perturbations. Computer arithmetic and numerical integration must be tested. A hazard assessment is an accumulation of small truths. No single correction changes Apophis from impact to miss today. Together, they allow confidence. The 2021 radar campaign was decisive because radar ranging directly constrained the dimension of uncertainty most difficult for optical astrometry. The returning echoes also produced coarse images. Each pixel represented tens of meters, remarkable for a target millions of kilometers away. The images suggested a bilobed shape, but they could not show individual small boulders or reveal the interior. 2029 changes the resolution scale. Radar at a much shorter distance can produce finer maps. Spacecraft can image the surface at centimeters or better depending on altitude and instrument. Laser altimetry can build precise topography. Radio tracking of spacecraft motion can estimate the asteroid's gravity and mass. Combine mass with volume, and density follows. Compare density with likely rock composition, and porosity emerges. If ordinary chondrite material has a much higher grain density than the asteroid's bulk density, the difference represents void space. Shape and gravity can reveal whether density is evenly distributed. A contact binary may have two lobes with different histories. One may be denser. The neck between them may be weak. Tidal stress could concentrate there. A boulder field on one lobe may respond differently from fine regolith on the other. The post-flyby spin state can reveal how torques acted on the shape. This is inverse science. Researchers observe motion and infer hidden structure. The asteroid cannot be cut open. Its response becomes the scan. Earth is the force that probes it. A simple solid body would respond predictably. A complex rubble pile encodes its interior in vibrations, deformation, and rotation. Don Quixote's possible surface measurements are therefore more than an engineering novelty. They can act like a medical sensor placed on the patient during a stress test. A tremor arriving from a distant landslide carries information about the path through the interior. Several sensors would be better, but even one can constrain timing and frequency. The companion spacecraft can observe dust clouds or newly exposed areas. Ramses can measure changes in shape. OSIRIS-APEX can map the settled aftermath. Ground radar can monitor global rotation. Each method sees a different consequence of the same force. The encounter may also produce dust around the asteroid. Loose grains given slightly more than local escape speed can leave. Because Apophis's escape speed is extremely low, a gentle disturbance may be enough. Some particles may remain temporarily nearby, following complex paths under asteroid, Earth, and solar gravity. Spacecraft navigation must watch for debris. The amount is expected to be limited, but uncertainty is part of the experiment. If a measurable cloud forms, its particle sizes and trajectories reveal surface strength. If none forms, the regolith may be more cohesive or the stress is weaker than expected. Dust carries optical consequences. A cloud can brighten the asteroid temporarily by increasing scattering area. Ground telescopes might detect a change in the light curve unrelated to rotation. Polarization can change. Infrared emission can reveal warm grains. The event resembles a very small cometary episode created by gravity rather than volatile ice, though no dramatic tail is guaranteed. Changes in rotation may be easier to detect. Apophis already tumbles, so its brightness pattern contains multiple periods. Earth's torque can exchange energy among the rotational modes. After the encounter, the main period may shorten or lengthen. The rocking motion may change amplitude. The orientation of the angular momentum vector can shift. These alterations affect future thermal forces and operational planning for OSIRIS-APEX. A spacecraft approaching a tumbling asteroid must predict where the surface will be. At Bennu, rotation was comparatively regular. At Apophis, navigation and mapping face a more complicated moving target. The close pass can make that motion even more complex. Mission teams will need rapid orbit and spin solutions after the flyby. Ground data and Ramses observations can help OSIRIS-APEX arrive safely. This cooperation illustrates another feature of modern planetary science. Missions are planned by separate agencies but inhabit the same physical event. Data standards, timing, communication, and observation priorities must align. One instrument may see what another misses. Ramses could fail to launch, or a companion could malfunction. OSIRIS-APEX could encounter an instrument problem after years in space. Weather could close major observatories. Radar transmitters can experience technical limits. Redundancy across nations and methods protects the science. The event cannot be postponed. Spacecraft construction schedules are not the only countdown. The asteroid itself is approaching according to celestial mechanics. Every day between now and April 2029 is a smaller number in the mission plan. For most people, the date is distant enough to remain abstract. For engineers, it is close. Hardware must be designed, tested, integrated, launched, commissioned, navigated, and placed near the asteroid. A cleanroom delay can consume margin. A launch vehicle issue can threaten arrival. Software must handle a rapidly changing gravitational environment. Small spacecraft must survive deployment and contact. International teams must rehearse operations. The phrase rapid mission is not marketing. It is a description of necessity. Ramses's construction milestone in 2026 makes the encounter feel more immediate. Carbon fiber is being shaped now for a spacecraft that may watch Earth fill the sky from beside Apophis. Electronics are being selected now for vibrations that may occur in 2029. A surface CubeSat is being designed now for ground no one has touched. These objects link the present to the future passage. OSIRIS-APEX provides another link to the past. Its sample return capsule is already on Earth. Scientists are studying Bennu grains while the carrier spacecraft travels toward Apophis. Material from one asteroid sits in laboratories. The spacecraft moves toward another. The solar system becomes a connected research program rather than a sequence of isolated missions. Bennu and Apophis differ. Bennu is carbon-rich, dark, and associated with primitive material containing organics and water-altered minerals. Apophis is stony and likely related to ordinary chondrites. Bennu's orbit posed a small future impact probability before detailed mission measurements helped refine it. Apophis once carried a much larger short-term probability before radar removed it. Both are rubble pile candidates. Both teach planetary defense. At Bennu, OSIRIS-REx measured the Yarkovsky effect with extraordinary precision. The spacecraft's gravity data, thermal maps, shape model, and sample improved understanding of how sunlight moves small bodies. Those lessons transferred directly to Apophis. At Apophis, the additional focus is tidal change. One mission studies two forces that gradually and suddenly alter near-Earth asteroid paths. Photons over decades, Earth gravity over hours. The contrast is elegant. The Yarkovsky effect is almost unimaginably gentle, yet long time magnifies it. The 2029 tide is strong and brief, and close approach magnifies its consequences. Planetary defense lives in both regimes. Slow drifts determine keyholes. Fast encounters reshape orbits. A mission must model them together. The same integration appears in the public view. People will see only a dot for a few hours. That dot carries decades of tracking, centuries of celestial mechanics, billions of years of geological history, and future lessons about deflection. A simple observation can contain many scales. The asteroid formed before Earth had oceans. It was moved from the main belt over immense time. It was discovered during one human lifetime. Its impact probability changed over days. Its risk was resolved over years. Its surface may shift in minutes. Its new orbit will last beyond civilization as we know it. The night of passage compresses those scales into one visible motion. Perhaps this is why close astronomical events feel different from distant ones. A galaxy millions of light years away is larger and more energetic than anything in the solar system, but it cannot approach us during an evening. Apophis is modest in cosmic terms. Its nearness gives it presence. It reminds observers that Earth is not separated from the solar system by a wall. We orbit among debris. Most is far away. Some crosses our path. Gravity continually negotiates distances. The planets have cleared much of their neighborhoods, but not all. Near-Earth asteroids are not intruders from outside nature. They are part of the same system that formed Earth. Some may have delivered water and organic material to the young planet. Others created extinctions. Impacts destroy and build. The Moon itself may have formed from a giant collision early in Earth's history. Cratering shaped continents before plate tectonics erased much of the record. Life evolved beneath a sky that occasionally delivered violence. Planetary defense is a new phase in that relationship. For the first time, one species can discover a potential impactor and intentionally change its path. DART proved the physical act. Survey networks build the warning. Apophis demonstrates prediction. The ability is still limited. We cannot stop every object under every circumstance. A large comet discovered months before impact would be extremely difficult. A small asteroid from the sun's direction may arrive without warning. A very large object would require enormous planning. But the principle is established. Asteroid impacts are natural disasters that may be preventable. They differ from earthquakes and volcanic eruptions because the source moves through space for years before arrival. With enough notice, the point of impact is not fixed. The future can be nudged. This creates a peculiar kind of responsibility. Once prevention is possible, failure to search becomes a choice. Telescopes and missions cost money, but the hazard crosses generations. A deflection mission may need to launch long before the predicted impact, perhaps before many people feel urgency. The benefits are invisible because success produces nothing. No crater, no blast, no headlines from the event that did not happen. Apophis's safe passage offers a visible symbol of that invisible work. The asteroid already misses naturally. No one deflected it. But the confidence to watch comes from investment in observation and analysis. The missions around it prepare for the day when observation leads to action. On April 13th, 2029, people may look upward and see not merely a rock, but a capability. We can find, we can calculate, we can cooperate, we can learn how to push, and perhaps, given enough time, we can prevent one of the oldest forms of planetary catastrophe. The site will still be quiet. There will be no planetary defense anthem from the sky, only a moving point. Its silence will leave room for interpretation. Some observers will think about ancient Egypt and the name Apophis. Some will think about satellites. Some will remember frightening headlines from 2004. Some children may decide to become astronomers. Some engineers working on the missions may stand outside after years of seeing the asteroid only as data and schedules. They will know where a particular instrument is beside that point of light. They may know that a small seismometer is resting on the surface, waiting for Earth's pull. Mission controllers will not experience the event as a simple night of watching. They will be receiving telemetry. Commands will be constrained by light time, spacecraft autonomy, and rapidly changing geometry. Every image may carry evidence. A boulder shifts. A dust plume appears. A signal drops. A rotation solution updates. The world watches one point while teams watch thousands of channels. The asteroid's nearest approach lasts an instant, but the operational event spans months. Before the encounter come the baseline measurements. During closest approach comes the maximum stress. Afterward come the surveys of change. The final scientific picture will emerge over years. Researchers will compare simulations and data. Papers will disagree about mechanisms. Laboratory experiments will reproduce granular slopes under variable gravity. Mission archives will support discoveries not anticipated when instruments were designed. Apophis will pass quickly, but understanding will be slow. This pattern is common. Cassini flew through Enceladus's plume, and data continued producing discoveries after the spacecraft was gone. Voyager passed the outer planets in days and transformed science for decades. DART struck Dimorphos in seconds, and analysis continues. A brief encounter can become a long intellectual object. Apophis may define rubble pile geophysics for a generation. The asteroid is also likely to receive unprecedented media coverage. Live images from spacecraft could show Earth behind a tumbling landscape. Radar maps may be updated in near real time. Observatories may stream the moving point. Public maps will show altitude comparisons. The temptation to present every signal as dramatic will be strong. If Ramses detects a vibration, it may be called an asteroid earthquake before the mechanism is understood. If a bright patch appears, headlines may announce that Earth cracked Apophis open. If no visible change occurs, some may call the mission disappointing. The scientific interpretation will be more careful. One vibration may be a spacecraft contact effect. One bright patch may be viewing geometry. No change may set a strong lower limit on cohesion. The best communication will let uncertainty remain visible. The history of Apophis demands it. A story that began with misunderstood probability should not end with exaggerated geology. The truth is already compelling because the outcome is unknown in the right way. The orbit is safe. The physical response is open. We do not need uncertainty about survival to create suspense. We have uncertainty about a world. Will it shake? Will it slide? Will its tumble reorganize? Will dust leave the surface? Will a contact binary neck flex? Will the interior transmit seismic waves? Will fresh, ordinary chondrite material appear? Will models of weak cohesion survive the test? These are questions with measurements waiting. This is scientific suspense. It does not threaten the listener. It invites attention. That balance is especially suitable for a quiet night. One can rest with the knowledge that Apophis will miss while imagining the precision required to know that. The safety is not an empty ending. It opens the deeper story. Return now to the evening itself. The date is Friday, April 13th, 2029. The sun has set for observers in parts of the Eastern Hemisphere. Twilight deepens. Familiar stars emerge one by one, though city light hides the fainter ones. Apophis is already approaching. For days, professional telescopes have watched it brighten. Ramses, if the mission proceeds as planned, has been beside it for weeks. Small companions have separated. Instruments have measured the initial surface. Osiris Apex is taking long-range images while continuing toward its later rendezvous. On Earth, observatories prepare tracking sequences. Radar transmitters and receivers coordinate. Amateur astronomers check clocks. Families and students gather in open spaces. Some people know the whole history. Others have heard only that an asteroid will pass closer than certain satellites. The point appears. Perhaps someone mistakes it for an ordinary star. A guide identifies it. Watch there. Wait. The position changes. Once motion is noticed, it becomes difficult to ignore. The background stars remain arranged in their ancient patterns while Apophis travels across them. The asteroid is not actually passing near those stars. They lie light years away. The apparent crossing is a projection of one nearby object against a distant sky. Every few moments, the geometry changes enough to see. Earth rotates beneath the observer. Apophis moves through Earth's neighborhood. The sun illuminates one side of the irregular body. Its tumble changes the reflected brightness. A person with binoculars may notice the point very subtly. A camera taking a long exposure records a trail. A sequence of short exposures shows the asteroid stepping across the frame. The experience is both immediate and delayed. The light reflected from Apophis takes only a fraction of a second to reach Earth at closest approach. What you see is almost now by astronomical standards. The starlight behind it may have traveled for decades, centuries, or longer. A nearby relic moves across ancient light. At the same moment, spacecraft see another view. From beside Apophis, Earth dominates. The planet's angular size grows rapidly. The Moon contributes a smaller gravitational influence to the exact encounter geometry, though Earth overwhelmingly dominates the flyby. Earth's night side glows with city lights if the angle permits, while the sunlit portion shows blue ocean and white cloud. The asteroid has passed Earth before over millions of years, but perhaps never at this distance during its current history. It has no awareness. Its particles respond to force. The nearest side accelerates slightly more than the far side. The difference acts across hundreds of meters. The entire center of mass follows the bent trajectory, while internal pieces experience small relative changes. On a stable slope, one grain presses against another. As effective gravity rotates, the balance shifts. Friction holds until it does not. A pebble moves. It touches another. A small cascade begins. Elsewhere, nothing changes. Inside, contacts tighten and loosen. If the body contains two lobes, stress passes through the neck. The surface CubeSat listens. Ramses photographs. Ground radar records a new spin signature. The strongest tidal interval passes. The asteroid reaches minimum distance. No line is crossed in space. There is no sign announcing geosynchronous altitude. There is simply one moment at which distance stops decreasing and begins increasing. Apophis has missed. It was always going to miss in the known trajectory, but the geometric fact is now complete rather than predicted. Earth's gravity continues bending the path as the asteroid departs. The point moves onward in the sky. Its solar orbit is no longer the same. Before the encounter, Apophis travels around the Sun in less than a year. Afterward, it takes more than a year. The asteroid leaves the Aten family and enters the Apollo family. A classification changes because a planet passed nearby. Its spin carries the memory of the tide. Its surface may carry new scars. Its orbit carries a permanent gravitational signature. The observers on Earth see only the point fading. Data reveals the transformation. Soon the asteroid's apparent position approaches the Sun in our sky, limiting ground-based optical viewing. Spacecraft retain their advantage. Ramses remains near enough to compare. Don Quixote, if safely attached, continues sensing the aftermath. OSIRIS-APEX closes the distance. Weeks later, the NASA spacecraft arrives to begin its extended survey. The public event ends. The science deepens. Maps from before and after are aligned. Boulders become landmarks. A stone that moved by a meter can be identified. Crater rims reveal small changes. Spectra show whether fresh material emerged. Thermal measurements reveal altered dust. The rotation model is rebuilt. Seismic records are matched with images. Some predictions succeed. Others fail. The asteroid teaches through difference. Suppose landslides occur mainly on slopes already near instability. That supports one model of regolith friction. Suppose movement occurs in unexpected regions because the changing spin dominates the direct tide. That supports another. Suppose dust is released from the neck between lobes. That constrains internal geometry. Suppose no global shaking is detected, but local cascades appear. That reveals rapid damping. Suppose the entire body changes its tumbling state, while the surface remains mostly fixed. That separates torque from deformation. Every result enters future hazard planning. If another 300-meter stony asteroid is discovered on an impact course, scientists will ask whether its structure resembles Apophis. If so, observe tidal and thruster responses improve deflection models. If not, the differences identify what must be measured before action. Planetary defense becomes empirical rather than purely theoretical. We will have pushed one asteroid deliberately with DART. We will have watched Earth pull another naturally. We will have collected samples from Bennu. We will have followed Apophis before and after a close encounter. Each mission adds a piece. No single experiment solves the entire problem. Together they create capability. There is comfort in this, but not in vulnerability. The solar system still contains unknown objects. Surveys still have blind regions. Deflection still requires warning. Technology can fail. Political decisions can arrive late. A very large or fast object would remain challenging. The correct conclusion is not that humanity has conquered asteroids. It is that asteroid impact is no longer an entirely passive fate. A door has opened between prediction and prevention. Apophis stands in that doorway. Its history shows the full chain. Discovery, uncertainty, risk, observation, resolution, preparation, experiment, learning. The missing step, deflection, is unnecessary for Apophis because the asteroid already misses. DART demonstrated it elsewhere. A future real threat would join the chains. The ability to combine them is one of the quiet achievements of modern civilization. It depends on astronomy performed night after night, often without drama. A telescope images the same field twice. Software finds a shifting dot. An observer schedules follow-up. A measurement enters a database. An orbit analyst tests solutions. An engineer studies launch windows. A committee funds a mission. A radar operator sends a signal. A spacecraft camera opens. None of these acts alone looks like saving a world. Together they can. Apophis gives those invisible acts a visible object. When the moving point crosses the sky, it represents thousands of measurements that turned fear into certainty. The asteroid's path is not visible as an equation, but the safe miss is the equation made real. The same night can also remind us why uncertainty should not be mocked. In 2004, scientists did not know enough to rule out impact. They said so. Later, they learned more. The answer changed. This is sometimes described as science being wrong and then correcting itself. A better description is that science reported the state of knowledge at each stage. The early probability was not a failed claim that an impact would happen. It was a correct claim that the data allowed a significant chance. The later exclusion was not a retreat. It was the result the observing program sought. If every early uncertainty were hidden until complete certainty arrived, follow-up would suffer and public trust would become fragile. If every early probability were announced as destiny, panic would replace understanding. The history of Apophis lies between those extremes, open enough to reveal concern, careful enough to revise it, patient enough to finish the measurement. The Asteroid also teaches that a dramatic date can be scientifically ordinary. Friday the 13th carries no force. The name of a chaos serpent carries no force. Headlines carry no force. Earth's gravity carries force. Solar heating carries momentum. Rock contacts carry stress. Photons return to telescopes. Radio waves return to antennas. Nature responds to physics, not symbolism. Humans can enjoy the symbolism without confusing it with cause. This may be one reason the event belongs so naturally to the night sky. People have always placed stories among stars. Constellations carry heroes, animals, monsters, and gods. Apophis carries an ancient name through a modern calculation. The old story imagined chaos threatening the sun. The new story watches a predictable stone pass safely through a measured corridor. Myth and mathematics share the sky, but only one predicts the distance. The ancient name remains beautiful. The modern orbit keeps us safe. Perhaps the most unusual part of the night will be how normal the world feels. Traffic continues. Oceans move under lunar and solar tides. Satellites relay messages. People sleep beneath the trajectory. No alarm sounds. The asteroid passes at cosmic speed, but daily life remains unchanged. A natural object capable of regional destruction occupies near-Earth space, and the event becomes a public observing opportunity. That calm is earned by knowledge. Without the orbit calculation, the same sight would be terrifying. With it, the sight becomes wonder. This difference is not psychological decoration. It is practical power. Knowing where an asteroid will be allows evacuation in a short warning case and deflection in a long warning case. Knowing where it will not be prevents needless action. Precision protects in both directions. False alarms consume trust and resources. Missed hazards cost lives. The purpose of planetary defense is not constant fear. It is accurate discrimination. Apophis is not dangerous now. Another object may be. The system must tell the difference. This is harder than simply finding rocks. A near-Earth asteroid is defined by orbit, not immediate danger. A potentially hazardous asteroid meets size and proximity criteria, not a prediction of impact. The label means it deserves monitoring. It does not mean collision is expected. Apophis remains physically capable of causing harm in a hypothetical impact, but its known path excludes that scenario over the assessed interval. Language matters. Potentially hazardous describes a category. Impact risk describes a trajectory and uncertainty. A large harmless flyby can belong to the first while having zero meaningful current risk. The distinction can prevent unnecessary anxiety as surveys discover more objects. The future will contain many brief headlines about non-zero probabilities. Most will disappear. One may not. The public lessons from Apophis will be tested repeatedly. Wait for data, but do not ignore probability. Ask how long the observation arc is. Ask when the object can be observed again. Ask whether the probability rose because the path narrowed. Ask what size is estimated and how uncertain it is. Ask whether the risk is regional or global. Ask whether a mission has time to act. These questions are more useful than asking whether an asteroid is a doomsday rock. Apophis was never a doomsday object. Even in the hypothetical impact case, it was a regional catastrophe, not the end of humanity. Accuracy in consequence is as important as accuracy in orbit. Overstatement can make smaller impacts sound harmless by comparison or cause people to dismiss all warnings as sensationalism. A city or region does not need a mass extinction to face disaster. Planetary defense covers many scales. At the smallest, civil defense, and window warnings may reduce injuries from an airburst. At intermediate sizes, evacuation and impact location forecasts matter. With longer warning, spacecraft deflection becomes possible. At the largest, international mobilization is required. Apophis helps connect these levels because it is large enough to motivate space missions, yet close enough to observe safely. The asteroid also offers a reminder that prevention can serve pure science. Ramses is built for planetary defense, but its measurements address planet formation. Rubble piles are not merely hazards. They are records of how small bodies broke and reassembled. Their porosity reveals collision history. Their boulder distributions record fragmentation. Their surfaces preserve space weathering. Their binary shapes may reveal spin-up and gentle contact. By watching Apophis respond to Earth, scientists study the mechanical processes that built planets from smaller pieces. The early solar system contained countless close encounters. Planetesimals passed planets. Tides stretched bodies. Fragments collided at low speed. Some joined, some separated. The 2029 event recreates one small part of that ancient environment under observation. A planetary defense mission becomes an origin of world's mission. This dual purpose is common in science. The knowledge needed to push an asteroid begins with understanding how asteroids are made. The technology needed to track a hazard improves measurements of solar system dynamics. The radar used to protect Earth creates shape models of relics. Safety and curiosity reinforce each other. There is no need to choose between them. When Osiris Apex fires its thrusters near the surface, the excavated patch may show material less altered by solar wind. Its mineral spectrum can be compared with meteorites in terrestrial collections. Ordinary chondrites are common on Earth, but matching one to a specific known asteroid connects laboratory chemistry with orbital history. The asteroid's composition can reveal heating and parent body processes. Its surface may contain impact melt, fractured minerals, or grains sorted by motion. Ramses's thermal instrument can map how quickly regions warm and cool. The result helps estimate grain size and rock abundance. The Surface CubeSat can measure local properties impossible to infer remotely. Each instrument sees a different chapter of the object's history. The dramatic flyby becomes a frame around deeper geology. All of this remains connected to the same central question. Apophis is not interesting only because it once frightened us. It is a world, though a very small one. It has terrain. It has a day longer than Earth's. It has a complex wobble. It has sunrise and sunset across irregular ridges. It may have two lobes joined by a neck. It may contain voids large enough to hide between boulders. It has no atmosphere, no liquid water, and no weather in the terrestrial sense. Yet its surface evolves. Micrometeoroids strike. Radiation darkens. Thermal cycling cracks rocks. Rotation moves grains. Planetary tides may rearrange slopes. A spacecraft will disturb dust. Small worlds are not static. Their changes are simply governed by forces different from those shaping Earth. On Apophis, a gentle touch can have lasting consequences. A grain lifted centimeters may take a long arc before landing. A boulder barely unstable may roll in slow motion. Dust can escape because gravity is weak. Footprints, if a human could somehow leave them, might last for ages unless a landslide buried them. The 2029 tide may erase some old arrangements and create new ones. The surface after Earth may remain changed for millions of years. Our planet will leave a mark without touching. Gravity is contact at a distance in the language of classical physics and curved spacetime in general relativity. Either description leads to the same visible consequence. Apophis bends around Earth. The closest approach is not merely a miss measured in kilometers. It is an interaction. Earth and asteroid exchange momentum. The asteroid's orbit changes. The asteroid's spin may change. The asteroid's geology may change. The term flyby can sound passive. This one is active. The body does not simply pass a stationary landmark. It enters a gravitational field and leaves transformed. Spacecraft gravity assists use the same principle deliberately. Voyager gained speed from giant planets. Cassini used Venus, Earth, and Jupiter. OSIRIS-APEX uses planetary geometry to reach its new target. Apophis receives an unplanned Earth gravity assist. Its new orbit carries it farther from the Sun on average. The encounter writes a new chapter into a path already shaped by Jupiter and earlier planetary interactions. No orbit is isolated. The solar system is a long conversation in gravity. Most exchanges are subtle. Close approaches speak louder. We happen to be present for this one. The chance to witness it raises another question. How many ancient close passages occurred above human ancestors without notice? A similar asteroid may have crossed within geosynchronous distance before writing existed. It would have appeared as a moving star. Perhaps someone saw it and incorporated it into a story. Without records and orbit calculations, the event vanished from history. The rock continued. The 2029 passage will not vanish. It will be recorded from the ground, from space, and perhaps from the surface itself. Its trajectory will exist in databases. Images will be archived. Children not yet born will analyze the measurements. The encounter will become a reference date in asteroid science. Before Apophis. After Apophis, models of tidal encounters will be tested against it. Future mission proposals will cite it. Planetary defense exercises will use its lessons. The human memory of the event will outlast the moving point in the sky. This is one way technology changes our relationship with rare phenomena. A generation can inherit detailed knowledge from an event no one can repeat. Solar eclipses recur. Comets return. Apophis will not repeat the same close encounter on a human schedule. The data becomes the encounter for future researchers. Preserving it matters. Raw images, calibration files, spacecraft telemetry, radar echoes, timing records, and amateur observations all carry value. A later analytical technique may extract information no one recognized initially. A better-shaped model may reveal a subtle deformation. A new seismic method may reinterpret Don Quixote's vibrations. A future mission may compare another asteroid with Apophis. The observing campaign should therefore collect broadly, not only answer today's questions. Cassini's archive produced discoveries after the mission ended. Apophis can do the same. One must also accept that missions may change before launch. Schedules, instruments, partnerships, and budgets evolve. Ramses is under construction in 2026, but spaceflight remains difficult. OSIRIS-APEX is active, but it must survive years and additional solar passages. The narrative should distinguish plans from completed events. It is honest to say what agencies intend. It is not honest to describe future measurements as guaranteed. The asteroid's safe trajectory is far more certain than the success of any particular spacecraft. Ground observatories provide the baseline even if missions encounter problems. The scientific opportunity cannot be lost entirely, though in situ details depend on hardware arriving. This uncertainty adds another form of suspense without inventing impact danger. Will the spacecraft be ready? Will the surface CubeSat land? Will Earth's tides trigger measurable motion? Will radar resolve the shape? Will clouds hide the naked eye view from a particular city? These are open. The miss is not. Clear reasoning can separate them. Certainty where certainty exists. Possibility where possibility remains. The final days before April 13th will likely bring a flood of public questions. Could the orbit be wrong? Could another asteroid hit it and change the path? Could Earth's atmosphere pull it in? Could satellites disturb it? Could it suddenly break apart? The answer to the first is that the trajectory is measured with extraordinary precision and will be refined further. The uncertainty is tiny compared with the missed distance. A collision with an unknown object large enough to redirect Apophis during the final approach is fantastically improbable and would itself be observable. Earth's atmosphere does not extend with meaningful drag to 32,000 kilometers. Satellite masses are negligible, and their paths do not threaten the asteroid. Tidal forces may change spin or surface, but they do not turn a safe center of mass trajectory into impact during the encounter. Physical questions are welcome. Fear often shrinks when mechanisms are explained. The asteroid is not guided by intention. It cannot choose Earth at the last moment. Its motion is continuous. Every new observation confirms the path. By the time it becomes visible to unaided eyes, professional instruments will have followed it with far greater precision than any observer needs for safety. The public can look up without waiting for a final minute announcement. There will be no countdown to impact. There may be a countdown to closest approach. The distinction is everything. A countdown to a safe scientific event creates anticipation rather than dread. It can unite people across countries under one moving object. Potential observers across the Eastern Hemisphere will not all see it, but the shared possibility is extraordinary. The track crosses regions with different languages, religions, and histories. The asteroid carries an Egyptian name filtered through Greek, discovered in Arizona, recovered in Australia, tracked by observatories around the world, approached by European, Japanese, and American spacecraft. Planetary defense is international because the sky is. No nation owns the orbit. No border redirects the path. The event offers a small image of cooperation built around a common physical reality. The data from one observatory improves safety everywhere. A spacecraft launched by one agency answers questions relevant to all. An amateur timing and occultation contributes to a global model. The work is distributed, but the target is singular. Perhaps the most hopeful part of Apophis is not that it misses. Most asteroids miss. The hopeful part is that people noticed, measured, communicated, and built tools before certainty was emotionally convenient. The early risk was allowed to be real. The later safety was demonstrated. Missions were designed not from panic, but from opportunity. The asteroid became a teacher. By the time it arrives, a quarter century will have passed since discovery. Some scientists who analyzed the first frightening orbit may have retired. Students who were children in 2004 may lead 2029 operations. A new generation will see the result of patient observation begun by another. Planetary defense naturally crosses generations because orbital warning times can be long. A threat discovered today may be addressed by engineers not yet trained. A mission launched years from now may protect people not yet born. This makes sustained institutions essential. One cannot rebuild the entire survey and response system only after an impact probability appears. The telescopes, databases, expertise, rockets, and agreements must exist beforehand. Apophis kept attention on that need. Its name remained famous after the danger disappeared because the close pass remained extraordinary. Fame can be useful when it supports preparation. The 2029 event may influence funding for surveys and missions more effectively than abstract statistics. People support what they can imagine. A moving point closer than geosynchronous altitude is imaginable. A risk distribution for unknown near-Earth objects is not. The challenge is to turn attention into durable capability rather than one-night excitement. After Apophis fades, surveys must continue. Ramsey's lessons must be applied. Osiris Apex data must be archived. Deflection methods must be tested further. International exercises must repeat. The sky will return to looking calm. The population will remain. The final scene can now be quiet. Apophis is moving away from Earth. Its brightness has faded below naked eye visibility. The people in dark fields pack binoculars and return home. Mission teams remain at consoles. Radar echoes weaken with distance. The asteroid's new orbit begins its first circuit. On its surface, moved grains settle. A fresh patch cools after sunlight. A small spacecraft listens. Another approaches. Earth continues around the sun. No crater marks the encounter. No city is damaged. No emergency is declared. The result of the night is knowledge. We learn how closely a large asteroid can pass without danger. We learn how a planet reshapes a rubble pile. We learn whether the surface moves. We learn the interior through response. We learn how missions cooperate under a deadline. We learn how accurate observation turns uncertainty into safety. And we learn what it feels like to see a former threat become a scientific guest. Apophis will not be the last near-Earth asteroid to attract attention. It may remain the most memorable safe flyby of our era. Years before it arrives, the date is known. Years after it leaves, the data will remain. The point of light will cross the sky only once. The lesson can continue. There is a stone moving through the solar system tonight. It is not yet bright enough for unaided eyes. It follows the orbit measured from Earth. Every revolution brings it closer to the encounter that once frightened astronomers and now draws spacecraft. It carries no message. It carries old minerals, fractured rock, and the memory of collisions. Human beings have supplied the meaning. Threat, measurement, test, opportunity. When the asteroid comes close, Earth will pull it into a new path. For a few hours, the ancient rock and the living planet will share one gravitational event. Then they will separate. The planet will keep almost no physical trace. The asteroid may carry the encounter written across its surface and rotation. And observers will remember a moving star that came closer than many distant satellites, close enough to see, close enough to change, but never close enough to harm us. Good night.